So welcome everyone to today's presentation about new architecture to be supported by Valgrind in near future. My name is Ivo Reiser and my colleague Tomáš Jedlička would like to present in 15 minutes. We both work for Oracle. We were working on Solaris previously, now we work on Linux. So this is just to say whatever I say here, it's uncovered. So why Spark? Because it's a cool architecture, and so we started with Solaris, and now we focus more on Linux. This is a brief overview of today's presentation. We will divide these palettes to Tomáš and me, and the beginning we will just share. So the story of Valgrind Spark port begins after the Solaris port was integrated successfully maybe 2 or 3 years ago. So we were talking with Tomáš. So Solaris is there, what's next? And Solaris on x86 or AMD64 was there, so what's next? So the obvious conclusion was, it's still missing the Spark. So because we were working on Solaris, so we started working on Spark on Solaris. Now we joined the Linux club, so we switched to the Linux, but still the Spark is the same. So we expect much quality use from the Spark Solaris port. And we maintain it as 2 separate forks, but we moved the code heavily between those 2 forks. And it's us, and with this whoa, it works. So now it's your turn, Tomáš.
Thank you. Yeah, so let's skip this slide. So, why Spark? Oh, what is Spark? So, Spark is a scalable processor architecture. The history starts in 80s. It was designed by Sun Microsystems. Today, it is still under development in Sun and Fujitsu. So there is a joint agreement between both companies that it will be developed in a way it is still compatible within each other. So that's why you can run Solaris also on Fujitsu Spark machines. Yeah, as you can see, a Spark hardware these days, it's not a small box. Actually, this was one of the older systems. So if you look, this piece is just a single Spark computer, which hosts like 32 terabytes of physical memory. And I guess this one has like 2,500 of hardware strands in it. So you can see a cluster of 2 of them, but the expectation is we will get to like 64 terabytes of physical memory and 4,000 of hardware strands in a single machine. So why the machine needs to be so big? Well, today not every kind of workload application is designed, it scales so well in a like the MapReduce style. So we still have a lot of applications which use a shared huge memory space that needs to be accessed from multiple threads. So this is why the Spark is still here and what the customers are expecting from the Spark. So the first thing we would like to quickly give you some introduction about how the Spark architecture works. So yeah, it must be quick because of timing, so it will be just the interesting parts relevant for Valgrind. So it is a reduced instruction set architecture. It means it has just a limited subset of instructions. All of the instructions are fixed sized, 32 bits. It is a load store architecture, so it means regular instruction cannot operate directly on memory. You need to load the data from memory to register first, then you can do whatever you want to and store it back again. Also, there are no things like implicit stack support you might be used to from the x86. So there is nothing like push pop in the function prologues. Basically, the stack is implemented by using general purpose registers, and it is up to compiler to manage or handle the stack frames and things like that. Common instruction on Spark has 3 operands, so it can be either 2 input registers or 1 input register and immediate value. And then there is an output register. So yeah, this is the most common format of instruction you will see. Yeah, the big challenge or difference is that the hypervisor, because the Spark machines support virtualization, but in a slightly different way you might be used to. So the hypervisor is actually built inside the firmware of the chip. So we can slice the big machine to smaller chunks, and each CPU is running in non-privileged mode, privileged mode which hosts the kernel, and hyper-privileged mode, which means it actually is inside of the hypervisor handling. Why it is important for Valgrind? It means the hypervisor is still there, and it takes care of some of things like interrupt deliveries all the time, and you will see it causes some issues for a user-land debugging, because it's firmware, so you can update it and it can alter the behavior of some of the functions of the chip. So how it looks like from the point of view of the register set. So Spark has a general purpose, it has 24 general purpose registers. I will have another picture, which are aliased into the input ones, output ones, and the local ones. We'll probably see it on the next picture. It serves for emulating of a function call. So we have something like input arguments, output arguments for the next function call, and the else are representing local variables in a function. But beyond that, there is a lot of more other, there are like really global registers. There are floating point registers, there are something called ancillary state registers, which is technically other kind of registers for other usage. And yeah, I will now peek to the next slide, try to explain more about what the I's, L's, and O's are. So from x86, you probably are used that the stuff is being pushed to the stack directly. What the Spark architecture has is it has many more registers than the number which is accessible at any single moment for the chip. So this is called a register window. So the I's, O's, and locals technically compose a single register window, which represents a single frame on the stack or function execution. So whenever you call another function from the caller, you will see that the CPU can allocate another window. So it will basically select a different internal registers and then perform translation of the I's, O's, L's to the new window. And you can see that there is an overlap, which means whatever you have put in the O registers are output arguments of your function. So after you call a function which will ask for a new window, the O's will automatically become ints. So in the next function, it will be in the I registers. I hope, does it make sense? Like, yeah. So the operation is called a save restore. So whenever you save, you are going to allocate a new window. If you call restore, you are basically freeing the window, unwinding the mechanism back. The issue here is that this is all happening inside the chip. So you cannot observe this behavior on the stack, unless when the kernel or the debugger explicitly dumps the data to the stack, or if you arrive to a place where you basically allocated all of the windows, so there is no other place for the next function call. At that point, a CPU will issue some spill fill traps, asking the system to actually dump the windows somewhere to the memory, and then either or reload them back as necessary. So after you fill all the 8 or 7 windows, you will start seeing the old ones being pushed to the stack, available for the debugging software. So yeah, this is quite tricky, and especially for Valgrind, it gives us a lot of headache to try to emulate this behavior on the guest state. Yeah, you can see the globals are always the same. So they are not affected by the window switching mechanism. Yeah, floating point registers, there is a bunch of floating points sized from 32, 64 bits and up to 128 bits, but they overlap. So like a double precision register is actually two adjacent floating point registers of 32-bit precision and so on. So this is another thing Ivo should be talking about slightly. Yeah, so this is about the register set. So next highlight of the Spark architecture is the control transfer. Spark is using a delayed control transfer, so it means whenever you branch to some different place, we are still able to execute one instruction after the branch before we get directed to new destination. So there is an example. You can see the branching works. For example, here we are branching based on condition codes. There are registers which holds the condition codes for us, and there is the destination. So technically this instruction is sitting in the branch delay slot and will be executed before the instruction at the new address. So this is part of the problem. Second part of the problem is you may have an annual bit here which says, but if we actually haven't branched, please discard the instruction in the delay slot. Because we are running on a RISC CPU, so everything is out of order inside the chip. So this instruction may have been prepared but not committed yet. And in case we didn't decide to jump, we need to discard this in the inside CPU buffers. So practical usage, for example, a compiler can put first instruction of the destination here and just said, but if we haven't jumped, discard it because I have preemptively executed something from the destination. Oh, sorry. So yeah, as you can see, this is managed by having two program counters. This is another difference from regular architecture. So you have a program counter which points to an instruction you are actually executing, and you have a program counter which is pointing to instruction you will be executing after this instruction. So technically it's always +4 because we have a fixed size, but in case of the jump you will see that the program counter will be pointing to the branch instruction and the next program counter will be the branch delay slot. After we execute the branching instruction, we will move to the next program counter, but we said that the next program counter will be at the address. So basically the transfer is handled by the two registers. And again, this is something which is not easily supported in Valgrind because there is no way or easy representation for this scenario. So yeah. Another nice thing about the Spark is whenever you try to load or store something from and to memory, we use a 64-bit address space virtual addresses. But we also have something called address space identifier, which is a 8 bits additional information telling the MMU how to alter the load and store so it can do something different. So some of the ASIs are designed for privilege or hyperprivilege mode only, but some of them are accessible from user space, which basically means you can ask the MMU, for example, to load data from memory, but switch NDNS. So the MMU will access the address in argument, but return you the reversed value in the register. So there are also other groups of ASIs, so some of them are calling a translating, which means we will involve MMU and use the address as a virtual one. Some of them are non-translating, which means they can reference a physical address. And there are, of course, a special ASIs, which allows us, for example, to address something which is not tied to address space like a registers. So, for example, Spark chip has more registers as a scratch space, so you can use ASIs to play with 8 extra registers if you need to have some spare place. Or for example, hypervisor can provide you special ASI for performance counters. So whenever you read something from a memory address with that ASI, you actually invoke a routine in hypervisor which will fill in the data for you, check whether you have a permissions and so on. So yeah, you can see the instruction itself is not different from a load store or regular load store, but can have a ASI in its in its opcode, which means if this is it, it's compiled in ASI. So we just say, do this load and use this constant. But to be more dynamic, you can also say just load from this address, but use whatever is in the ASI register of the CPU. So you can dynamically change what the current ASI will be by writing to the ASI register. So only at the runtime you know dynamically what actually this will do. Because, for example, there's a good example. This is something load float from memory, which will load 8 bytes by default. Yeah, by default mean there is nothing like this in the instruction. This works because a CPU has some notion of the default ASIs. So if you omit everything, we will use one of the default values, which is described in the documentation. But you can see whenever you put a different ASI to the instruction, it changes the behavior of the instruction, how many bytes it loads. Also, there are things like block stores and block loads, which will, for example, read 64 bytes from memory instead of 64 bits, and so on. So, yeah, this is basically the problem we have at VEX, that if it is not written there yet, we have quite a hard time to do some compile time translation of this address space. And also, we have a big problem in the memory tools, because the tools doesn't know nothing about what the ASI means. Some of them are even vendor specific, so they can be different between the implementation on Spark with different vendors. So, yeah, OpenSSL and other things can use it. Crypto instructions, Spark has a lot of crypto instructions built in the CPU. So they are, for example, using some special ASI to do the stuff. Okay. Yeah, this is new feature of the new Spark CPUs, the ADI. The logic is we are trying to detect memory issues in the code in the real time on the running chip. So what we do, we are actually using unused bits in a 64-bit memory address. So we can put a color on a pointer. The pointer is stored in the cache line and later in the memory DIMM module. And on each access, we are checking whether the color is still in match. So a CPU will issue a fault whenever there is a mismatch between the colors. And that way, we, for example, can put buffer boundaries by coloring different things in before and after the buffer and detect them on runtime. However, it's cache aligned, so it works for 64 bits. You cannot create a smaller chunk or smaller piece of memory. Yeah, usually for a user process, we deliver a asynchronous signal to signal that the ASI has been messed up, and it can be handled somehow. It depends on the tool. Yeah. I would say last thing, because on Spark, whenever you do a syscall, you need to have a mechanism to enter the kernel somehow. It used to be by issuing an interrupt. Now we use syscall, sysenter instructions. Spark is still using the trap. However, Spark has a hardware support for traps, so each time you trap, the context will change slightly in the CPU, so you have some fixed amount of nested traps you can create. So for that reason, if you do a syscall, it will jump or push the CPU to different trap level. We need to move it back to trap level 0 in kernel. We need to find a syscall, do the stuff. It's a lot of instructions and some work. So we use something called fast traps on Solaris, which basically allows us to create a syscall which is directly handled in the trap level context. So it's used for some really high-speed stuff like getting timers or something out of your process. So instead of doing this mechanism, we just directly trap, and at the trap level handling code, we handle everything and return back to the client, sometimes even without switching to privilege mode because it's not required. So this is also a big problem for us at the tool level, because we need to handle them differently. Yeah. So now
thank you, Tomáš, for introducing us interesting aspects of Spark architecture. And now I'd like to tell you quickly what parts of Valgrind are affected by Spark support. So this is my picture, so don't blame me. The most interesting part is, of course, done in VEX, because we need to provide a front end which does this translation from binary to intermediate representation, and we also needed to provide instruction selector and emitter to go from IR to back to assembly. So, and then there is a whole bunch of core-grained modules which needed to be hacked somehow. Some of them slightly, some of them quite heavily, to support Spark on Solaris or Linux. Then there is GDB support, which works over the GDB remote protocol. We had to provide support for this in GDB because it was not there. And for the tools themselves, there was not so much work required, only some work in memcheck to support some more IOPS, not much. So this is our guest layout. So you can see globals, outputs, locals, and input registers, as Tomáš mentioned. Then there is a whole bunch of floating point registers, some ancillary state registers, and then there is support for lazy evaluation of condition codes, registers for integer and floating point. So you can see we didn't emulate all the register windows like Tomáš described here. We emulate just a single one. Why? Because all the Valgrind machinery expects a stack pointer to be just an offset in the guest state. And because the stack pointer moves, stack pointer is one of these registers. And because stack pointer constantly moves in these register windows, so we cannot say, oh, this is the stack pointer, because it always changes. Also, one of the reasons is the user space program has no visibility in the other windows. It just sees one. And also, for other Solaris, I mean other OS specific problems, we need to synchronize the guest state to stack, to spill the register window, and it was very difficult to achieve it if we had all the windows. So we simulate only one register window, and we do immediate fill or spill based on how do we encounter save and restore instructions. So, and we have also some scratchpad here, which we use for loading and storing some of the ancillary state registers if they do not support moving between registers, but they also support moving between memory and register. So that was register window support. Instructions in branch delay slots need to be simulated carefully because of the annulling bit. So we have a kind of branching code which the front-end emitter front-end generates. This is simulated based on other architectures. They do it similarly. They lazy evaluate the condition codes. This problem Tomáš mentioned, if there is AC in the register, then we have no way how to tell at the translation time what the instruction actually does. So this problem is still not solved. we have just worked around it a bit. Also because memcheck does the shadow operation on 16-byte floating point registers, so it converts them to integer operations. So we had to provide some basic emulation of those byte integer registers in the instruction selection. We also get, like on the MIPS platform, we had hundreds of warnings from the compiler because of the misaligned access. And we have problem how to efficiently represent fast traps, which return up to 5 return values. So it's still to be solved. And we also evaluated the possibility if a Valgrind can leverage application data integrity somehow to check the addressability aspect of the program. Also, because load and store can be decorated with different ACIs, we had to put new attribute here in for the load and store operations. It's still questionable if this is the right way to go. I don't know. Basically, it means that all the tools which somehow instrument loads and stores will need to be taught about new things. For example, this specific address space identifier says, okay, you perform the load or store, but do not fault if there is a problem with addressability. So we will need to teach memcheck about it. And it is still not clear how. So there are still lots of open questions and problems to solve, and I hope to facilitate some discussion about these problems at this meeting. And the current status of the Solaris and Linux ports are, we have been working on Solaris port on Spark for 2 years, so it's quite mature. So memcheck basically works, the other tools somehow, and this month we have started port for Spark on Linux. So at this point just builds, nothing else, and that's it. Both ports live at this at this moment. They live at this address on Bitbucket repo under different branches. And I think that's it. So now we take questions and answers, if there are any.
For the register windows, isn't there some mechanism to do register arrays in Vex?
I know. There is support for get index and put index.
Yeah.
We have considered it, and we had this prototype with get I and put I, but it didn't work because there is no way how to get the current index from the user space. You have no visibility which window you are in.
What I would like to say, there are additional registers which are supposed to be those equal for the window mechanism. So there is a current window pointer, what windows we can save, restore, which or how many windows belong to different address space, because you definitely don't want to pass kernel stuff to the user land. So, but those of them are usually privileged access.
Yes,
so
yes.
The kernel can access, switch a window, read whatever it does, but it's not possible to do it from user space, except calling many saves and those just to put the system to dump the stuff on stack.
So we had no way how to tell which window it was, and we got lost.
So that means you just simulate one window, you do spill and restore
Exactly.
every function call.
Yes, yes. Yes, it is expensive because here the safe entry stores, the pushing window there and there is very cheap because it just switches between the internal registers. The only expensive way is when you encounter a fill or spill trap. But now we do fill and spill immediately, every single push or fill or spill. So it's kind of unfortunate, but we were forced this way. So for this reason, and also for the problems, because there are two program counters, so the current port is quite slow. I haven't done any comparison, but when I run something on x86 and on Spark, it's quite slow. So some performance optimization needs to be performed first. So, any other questions?
Okay. For the address space identifiers, when you said some of them are custom or
Vendor specific.
vendor specific,
Mm-hmm.
but what can programs rely on?
Yeah, well, I mean, you need to take a slightly different rule compared to say this safety because it's only compliance, but that is like an extension to the architecture. On Spark, we have a sparcv9, which is a top level common definition. Then you have a multiple platform, some for U, some for V, some for R, I guess some for M. And then you have a specific chip specified by the vendors. So at the top level is the only common thing you have. So ASIs and sparcv9 standard will be the common one for every vendor. But as you travel down the architecture, you may say, but if I know I'm running on some for V, there will be two additional ASIs I can rely on, and you need to know this if you are developing the software. But most of the ASIs are truly, because the ASIs, the lower half is privileged only, so it's meant to be used by the kernel level person. And even the supportion is just for the hyper. So there is not so much ASIs. I don't know, it's like 20 of them.
Oh, could be.
Or user line available, which will not cause privileged stuff, so you can use them.
So, but can't you then OpenSL, for example, will probably check all the hardware accounts? So OpenSL will check which processor is running on.
They are using the standard ones, which are defined in sparcv9. So the standard ones should be supported by all the vendors.
No.
So they are safe. But
Also, we have something also largely something like capabilities for symbols. So whenever you link the stuff, you can just say, I have a special version for this kind of CPU architecture, and the linker will pick the most optimized way from the binary. So during the link time, you can actually link inside a special code doing something different, but it is developed by us, so we know what we do. Like you can switch CPI version to something more optimized for a given architecture, and so on, so just pick the function for you.
so it's like
Actually, it's not enough to get the hardware capabilities in the auxiliary vector of the kernel.
Yeah, okay,
So-
but then can't you just strip everything out of there? Only emulate a very basic without any extra inside.
This is what Yoshi is doing. We actually replace the memcheck and stuff with a version which doesn't. We preload some functions to
Yes.
the binary to avoid this stuff.
yeah. So that's the workaround currently for now. But
So we dodged and it's a different.
so that's the workaround. Just avoid this stuff until we can solve it. But I fear the proper solution would be if we ever encounter write to this register. So we will probably basically end the basic block, and when this will be this block will be translated by VEX, we need to check the current register value with the expected one and provide the proper translation and have the ability to choose between different translations of the same basic block.
Yeah, that's the kind of thing the QA has to.
Exactly.
Yes, you have
Exactly.
multiple translations which have assumptions about
Exactly.
the state at which the machine is
So-
going to be translated.
That's probably the solution here, but it will be
That's a massive architectural change.
exactly
But yeah.
because all the translation caches and that stuff is now assumes there's just one basic block translation.
So how many different ASI values can there be? 256?
It's 8 bits.
8 bits.
For land, it's just about like 128.
Hmm. But all the different instructions have a limited set of identifiers, maybe 20 for every instruction. So it's
Most of them are changing the scope of the load. Like 1 to 0 memory, you would have to repeatedly write 64 bits to the memory to get the chunk 0. But you can write just one instruction and the SI tells wipe out like the 64 bytes of the continuous memory after this pointer. So this is most of the SIs I have seen do this stuff like blocking operations instead of like small chunks.
That's really horrible.
it is. It is. I don't know why they chose this way because hard to say. Maybe they are running out of opcode space.
It was a cool idea at the beginning, but it's been abused terribly.
It's like the delay slot idea. It's a cool idea.
It was, yeah, before
And
the
register windows.
systems, yeah.
Yeah, but now it's legacy, and you have to deal with it. But no one is happy about register windows and delay slot. It's
Yeah, yeah.
legacy in the architecture.
You need to wait for sparcv9.
What happens in sparcv9?
I don't know.
Okay.
Okay, and the other one.
Any question?
Yeah. How usable is the Linux port actually already? So would it actually, if I took the patch and put it in the Debian package, would it be?
No. You are too far ahead. There is no package yet. There is just.
No, I mean I could take right. We currently have a patch, right? That is basically that would be on top of the
Right.
upstream
Yeah.
version, and it would add something.
Yeah,
Just
so you.
wondering how usable that something is. And I could already give it to some.
Good question. Ask in a few months. Just now it built. That's it.
Okay.
That's it.
Have you not tried to run it at all?
We have tried, but there are still
It's not so easy to get
Still-
it running just after the
unimplemented functionality, and things which break for some reason, and you need to investigate. So, yeah, it's at the beginning. The Solaris port is quite ready. I have tried some complex programs and all the Cisco interfaces, and other problems are either solved or work around, so it runs, gives you some expected output.
So how big a program can you run on the Solaris core? Can you run OpenOffice?
Yeah, much more complex ones. Maybe like on the storage servers, they take gigabytes of memory, just code, and other gigabytes of other data.
So is this stuff getting used internally inside Oracle to find bugs? Or you can't tell me the answer to that?
Sorry.
Is it getting used internally inside Oracle to find bugs?
It is.
Or you cannot tell me the answer.
So the x86 port on Solaris is used heavily internally, and I have reports from people. They found it very useful, like in the Linux community. The Spark port is not so widely known, so I don't know. I don't know that.
The problem is you need to have a Spark, and it's not so easy to use.
Has there been any interest in the Lumos community?
Good question. I think Illumos runs only on x86.
There is some Spark support on one distribution. There's patches, variant code Windows setting actually to
Mhm.
run this file.
I don't know.
Around the clock and what?
Windows setting continuation like this files.
I don't know. I was in contact with some Illumos maintainers who are running regression tests on x86, and they package it in some distributions. I don't know about Illumos on Spark. So
But the stuff that's actually applicable to Solaris still kind of applies to the old practice. There's nothing actually Oracle specific, right?
okay.
It's based on the latest public stuff, I guess.
Yes, yes, yes.
We have a Oracle Spark architecture documents which are extended to the sparcv9, so it's like based on 2015, I guess.
Mhm.
There is maybe 2017 probably available public, I'm not sure about this. Yeah.
But we base it on 2015, which corresponds to M7 or T7.
The page coloring you're using for checking that the pages in memory, the process checks that they are consistent and that one is this taking advantage in Linux, and you can in Solaris it is, because in Solaris it checks and it says, okay, you go going out to the buffer, you go out of your this reserved space, and it kills the process. But I don't know if these things are Linux, for example.
So this is a Spark feature, so it can be enabled on Linux. I don't know what's the state of current state of how to enable it in Linux, but this feature needs to be enabled first, and it needs to have a support from the memory allocator, such as malloc in libc. So you basically tell somehow to enable this feature for this current program, and the allocator behaves slightly differently. Instead of just returning pointers like it used to before, it now returns colored pointers. So the topmost 4 bits contain the version or the color. And I don't know if the allocator in Linux libc is capable of that. Or
Not yet.
Okay,
The
okay.
kernel bits are being submitted upstream right now, and so they will land upstream very soon. And now we are working to have support in glibc as well, and also in GDP, so you can get a nice message.
Instead of getting a panic.
Yeah, one thing about Spark is the x86 has some debugging support in hardware for kernel engineers. Spark has a very little of debugging support, so you are not able to set damage point, for example, because there is no such debugging register when you can say, hey, if you touch this space, give me a fault. So this is actually way how we can introduce memory watch points for a kernel guys, so they will definitely want to download something like this. At least be able to debug kernel.
What is the random value of the checking? Is it the page or the cache line?
Cache line.
Cache line, 64
bytes.
Mhm. So, and basically, for small buffers, it's way too big. So they use clever technique, because you are usually interested in buffer overflows. So they position buffer at the end of the cache line, so you can detect the end of the buffer right.
You mentioned that you're implementing the next point counter, but I suppose not many applications will directly manipulate the point counter and the next point counter. So wouldn't it be possible when converting to intermediate representation to cheat, and basically when you have delayed instruction to expand it to a non-delayed instruction?
Let me repeat the question, because it was not clear here quite a lot. So the question was about if we can cheat and do not simulate or emulate the program counter and next program counter exactly like the processor does.
I think it's, well, you cannot simply write the program counter on Spark, because I think the next program counter is not even writable, it's just read only. So you need to issue a branching instruction or something like this to actually write something to the next program counter. So you will have to do this same on the backside. But I think at this moment there is no such check which will be regarding the legs to not do something malicious. So probably you will, if you try hard, you will find some way how to cheat the program counters from the legs and IR.
So when you have to hack the block disassembly logic so that when it sees a branch instruction, then it has to also pick up the instruction afterwards and then put the intermediate representation before it or something?
Exactly.
Yes,
We
exactly.
basically unwind the delay slot during disassembly phase in the order of the instruction. So if we know it's only going to execute, we revert the order into the disassembly. So we will put the delay slot in front of the branch and then issue the exits. Or we do stuff like side exit is here or jump over the exit for the annual bit. So part of it is just about changing the disassembly logic, but the annual bits require some complex handling.
So it sounds like it would be helped if you had a more flexible intermediate representation that could do conditional branching.
That would be helpful. Mixport does quite the same thing because they have also delay slot, but they do not have annual bit, so they have an easier situation. Okay, someone else? We have still 2 minutes, maybe. Okay, we are done.
Yeah.
So thank you for your attention and happy Valgrind.